Respected Director Sir of Tata Medical Center, Dr. Arun, ex-Director Sir, Dr. Mamin Chandi, who has joined us online, thank you. Respected ex-Director Sir and Professor of IIT Kharagpur, Professor Bhaktaprati Chakravarti, distinguished guests, and people who've also joined us online, friends, colleagues, a day that we should not be proud of, but be humbled, because it's a dream that's come true. Within the next few minutes, we'll try and present to you what was thought of, and then my colleagues will show you how joint collaboration between an institution which is just 11 years old and an institute which is a state-of-the-art from years after independence has joined and is gifting India its first oncology image bank, image repository. Sorry, can you please tell me if I can move the slides? Thank you. It was in 2011, May, that we commissioned Tata Medical Center for service to the nation. And within a year, the institution decided that it should have an ethics committee and the research review board. The then director was very keen that service, research, and education must move hand in hand. And the standards were that it should be meeting international ethical standards, and we should always do patient-centric research, not using patient money for research, but using research money to try and help patients across the world. Whilst we were doing all the service setup, SOPs were being set up, it was our collaboration with Professor Chakravarti and his team in the Department of Computer Science, IIT Kharagpur, that made us think and move out of the box. At the same time, the Department of Biotechnology floated the idea of the virtual National Cancer Institute being formed. And I still remember it was the three of us, the three stooges, if you might call, Rimpa, Indranil, and me. We were sitting in our desks and we were thinking, well, why can't we, along with IIT Kharagpur, form the virtual cancer institute that India needs? We put concept notes together, and with the support of the directors and also colleagues from IIT Kharagpur, who we started working with, we put in our first application, and that was the seed that was sown for this event. We're privileged to work with some of the experts in medical imaging from IIT Kharagpur. Professor Mukherjee from Jayanta Mukherjee from IIT Kharagpur had a keen interest in these medical imaging and predicting models. So the first question we had is, how can we predict response to a treatment using image analysis along with clinical data? So it's not isolated image analysis, it's data and image analysis together. Around the same time, we worked with our pathology colleagues, and Dr. Indu Arun, who is not here yet, I'm pretty sure she's joined us virtually. She worked with another professor in IIT Kharagpur, and we published in one of the best journals in the world on digital imaging in standardization of Ki-67. And this is what enthused us further. 5 years, we really worked hard, and believe you me, we had very little funding, but thanks to SERB, through an imprint project, we had funding for a lung cancer project, which has now been completed. The novelty of our concept withstood international peer review, and that is what made us feel that we are actually doing the right thing. We published in peer-reviewed journals. The tangible cost of the projects were covered by people with vision, and they were the directors of the two institutes then, Dr. Chandi and Professor Chakravarti. And they said, well, look, we've got some intramural funds. Why don't you do what you're trying to do? Because it makes sense. And that is what gave us the energy to work towards CHAVI. But bigger projects needed further funding support. Bigger projects needed further collaboration. And again, by 2018, our team in the Department of Radiation Oncology went up from 3 to 6. And we had the brains of Dr. Shantam, Dr. Tapesh, and Dr. Moses. And along with this, we said, why don't we think big? Why don't we try and aim and achieve India's first oncological image bank, which is futuristic, which is going to be hosting images, not just images, well annotated images. Outcome data will be available. And we stood with our colleagues in IIT Kharagpur, who actually extended a tremendous support. I went to Jayantada's room, I remember, and I said, Jayantada, what about an image repository? And immediately he said, look, I think this director is the best chance that we have. So why don't we try and see if we can actually move on to the director's office straight away? Went and met Professor Chakravarti, and we made an application through the Department of Science and Technology. We actually, and MHRD, we received this sanction letter. Straight away, went to a director's office in Tata Medical Center, and without much of ado, we actually went ahead and got the ethics clearance for the study. Now, the ethics clearance is important because it's not just a repository which hosts images, for retrospective images, loads of images lying around. But we said we want to be futuristic and patient-centric. So we want patient consent for every image that we bank in our repository. So these are all done. The flurry of projects that were initiated, some completed, they gave us the confidence, like I said. And I believe the time is right now to collaborate further and to improve the cancer outcomes. Ladies and gentlemen, a very good morning. India's first fully annotated, freely accessible oncology image bank is all there for you. May I request our director, Dr. P. Arun, to come and commission the image bank for us. Thank you. Shantam or Indranil around? Would you address first?
Oh, yeah, we'll do that. Thank you, Sanjay, for sharing the journey of CHAVI with us. And I'm delighted to be standing here to welcome a whole host of dignitaries, spanning not just medicine, but technology, computer science, and funding agencies like the SUR. So you give us the fuel to think and work harder. So to this program, I welcome Professor Partha Pratim Chakravarti, Dr. Partha Pratim Das, Professor Jayanta Mukhopadhyay, Dr. Agarwal. Thank you, sir. You're a Calcutta man. I can see the pleasure in your eyes whenever you visit Kolkata. Dr. Balachandra had the fortune to get acquainted today. Dr. Sudeep Gupta is here. Shaleen Kumar, Dr. Francis James, Dr. Thomas Ram, and a very important member who represents the community. It's Dr. Abhijit Kar. So a very warm welcome to all of you at TMC. It's a matter of pride that I stand here and when Sanjay announces that is the nation's first freely accessible, annotated, de-identified image bank. Data is key. And as doctors and scientists, the first data that we got our head around was genetic data. So there was a code to it. It took time to decipher that code. And today, many years down the line, we are in a position to play around with that code. We can edit that code. So if you didn't have information about the code in the first place, it wouldn't have moved any further than that, beyond the 4 letters AGTC. The evolution of fast computers, fast processors have brought many kinds of information to fore, but it also brought in an equanimity in the kind of data that we collect. So whether it be patient data, whether it be the genetic code, whether it be pixels from an image, current developments have brought them together on a platform And instead of research being multidisciplinary, it brings focus into an interdisciplinary kind of research. And that is the way forward. So I believe it's baby steps today. You have a bank, and our team from radiation oncology, Sanjay, Indranil, Rimpa, Shantam, Tapesh, Moses, they have shown that you could bring out information from these images which would be relevant to clinical practice. But being limited to Tata Medical Center probably or definitely has its limitations. And that's why we have opened it out to the world. But releasing data has its strength. At the same time, it's also important to know how this data is used and managed. If you have online banking today, the chance of it being misused have also come. So a great deal of vigilance also needs to come when something is given up for free and when it is available. I'm sure the team, in collaboration with IIT Kharagpur, would put in requisite safety and ethical standards into whatever research comes out of this data bank. It also brings a philosophy to fore, where if doctors work alone, that's so far that we can walk. It's time for us to reach out to people whose brains work in a different way. And IITs being the premier institutes, IIT Kharagpur being one among the foremost research centers of the country, it's but natural when TMC and IIT Kharagpur come together, good things would happen. And I'm sure at the end of it, there would be a recipient of all the efforts that we do, all the long hours that they spend on this project, with all the passion that they expend on this project, that at one time, our collaboration will lead to something that would bring us even a minuscule of change would be a great change in the life of a patient with cancer. I also see Dr. Maman Chandi on the screen today, and this institute has developed its own philosophy over the past 10 years, and in a direction which Sanjay so eloquently expressed, that our primary job here is treating patients, but at the same time, we have a responsibility of improving his life and to bring in newer technologies and newer programs as we move along. So I also take this opportunity to thank Sir, who has been a guiding light for our institute. With those words, I stop here. You have a long program ahead of you. And Sanjay, please take over. And thanks so much for being in TMC with us today.
Thank you, sir. The next person is someone who really we miss quite a lot, isn't it? I mean, the gentleman was here a few days ago, and he was in his office, and he was, we used to run to him, sir, can we have approval on this, and then get his advice. And obviously, we owe a lot to Dr. Chandy, Professor Mamin Chandy. So, sir, it's all yours. Please, can you address us on your views on CHAVI and how to take this forward?
Sanjoy, thank you very much. Uh, I'm very happy to be here with you at the inauguration of CHAVI. Now, I want to express my gratitude to the Department of Radiotherapy, Sanjoy, Indranil, Rimpa, Moses, Tapesh, Santam. I don't think I've left anybody out, but all of you have worked very hard to put this together. I also want to acknowledge our colleagues at IIT Kharagpur. I especially want to acknowledge Professor Partha Pratim Chakravarti and his willingness to collaborate. Now, usually, a person who is the status of the director of an IIT in India will have many uh, questions as to whether something can be done, what are the problems, how will we do it, not Partha Prati. I have never come across a director of an institute, engineering institute, who was so open, so ready to help, so happy to collaborate with us. And without his help, I do not think we would have started some of the courses that we have started, for which India truly needs the HR to move forward. So, Partha, my personal thank you to you for having supported TMC in our collaboration with IIT Kharagpur, and I do hope that this will go forward. Yesterday, I was going through the TCIA, which is the image bank of the National Institute of Health, and it completes 10 years today. And I was amazed at the amount of anonymized, annotated data which is available on the TCIA. I was even surprised that they have an area where software engineers can look at the database and see how to improve the mining. Now, when you mine for gold, you are going through earth, and you are lucky if you find gold. Now, when you're mining data, the data is only earth. There is no gold there. It is just earth. But if you mine that data correctly, you can discover gold. You can make gold out of earth. So that, I think, is the importance of these international anonymized patient databases, which have everything from clinical history to imaging to molecular diagnosis and histopathology with all the immunohistochemistry, and then treated on a particular platform with outcomes data. I was looking at 600 cancer patients contributed by Duke to TCIA, and it's amazing, everything is there. So you might say that, okay, as artificial intelligence looks at the texture of the image in a particular subset of breast cancer, this may do well with this type of treatment, because I also have molecular data which supports that this molecular change may be associated with this MRI change on the imaging. That is where the world is going to go. And I'm happy that CHAVI will be India's first contribution towards this international effort to use data to try and improve outcomes. I think there is no doubt that all of us are in this business to see whether our patients can have better outcomes. And that makes all of this meaningful and worthwhile. That our ultimate goal is that we will make a better diagnosis, we will offer a better treatment with less side effects, and our outcome will hopefully be cure. So, congratulations to the radiotherapy team, to IIT Kharagpur and their collaboration, and particular thanks again to Sanjoy and his team, and to Partha for having been such a source of help to Tata Medical Center. Thank you.
Thank you very much, sir. I think sir's just told us a lot about Professor Chakrabarty. No doubt, he's a man who we approached with quite a lot of questions. And it has not ever been possible. This could not have been possible without his help. He has always welcomed us, and he's extended support. And I think, on behalf of all of us, we would like to welcome him to address us on CHAVI. Sir.
Thank you, Sanjay. Professor Chandy, Dr. Arun, Professor Agarwal, and all the dignitaries who are there, and the core team of CHAVI, guests. About 20 years ago, while IIT Kharagpur has been doing research in medical science and technology since the beginning, you may know that Dr. Mani Bhaumik of the laser fame was a PhD from IIT Kharagpur. But about 20 years ago, it was envisioned that in the gamut of an IIT system, the next 100 years is for collaboration with technology and medical science. So IIT Kharagpur opened up a school of medical science and technology about 20 years ago, Jyotirmoy. So it's about more than 20 years that the School of Medical Science and Technology opened up, where doctors would come and learn technology. The objective was that in the same laboratory, a technology scientist, a computer scientist, and a doctor would work together. That brings a different dimension. Through these years, we learned that the doctors, being computer scientists, through these years, we started learning that while we are progressing forward, we realize that computational medical science is moving from assistive to autonomy. And this, as Dr. Arun mentioned, needs to be charted correctly and carefully. The first learning that we had, which was obviously a little thing that took us, a new learning, because we thought we computer scientists are the most sought after people in the world. We realized that the doctors pick up computer science faster than we pick up medical science. So soon as things started happening, the reason for this collaboration was twofold. One was the enthusiasm, the energy, and the willingness to go 3 steps forward by Tata Medical Center. And the realization of IIT Kharagpur is that howsoever big an institution you may be, if you don't work with the best in class in every domain, we are not going to learn anything. So this started the collaboration which Dr. Chandy so kindly mentioned, but I would like to again reiterate that when you work with a big quote unquote bureaucratic institution, the amount of struggle that the stakeholders have is large. And I'm really, really grateful to the Tata Medical Center team for being so proactive and so working together. Now, I am a computer scientist, and therefore we all know, as you have already heard Sanjay, Dr. Arun, and Dr. Chandy say, that use of computational sciences and artificial intelligence, creating data, generating data is going to be absolutely essential. The effect of this project, which was taken up, was because most of the data is not Indian data. The data that we typically tend to have is all data in NIH is all other Caucasian data, this data, other data. And Indian data is all available in pockets. So the goal was that we not only need to create a fully annotated set, we need to make it public. We not only need others to use it, we now want others to contribute to it. This will enable us, at least the cancer doctors all over the country and all over the world, to get access to data, to add more data, to add more knowledge to the data. This is nothing. This is just a drop in the ocean. So in order to do this, when like you just heard the 6 musketeers here who are working hard, when this project idea came to me, whenever you're in trouble and you don't know what to do, you go back to your college mates. So I had 2 college mates, Professor Jayanta Mukherjee and Professor P.P. Das, who were the absolute experts in this topic. And the other advantage of having such people is that you can not only delegate responsibility, but if you tell them something which is not worth saying, they'll come back and tell you this is not right. This is what is the reason for success. Otherwise, when you are the boss of an institute, everybody will come and tell you, first hear what you want to say and say that is the right thing. So you need people who will come and tell you what is the right thing according to them. And over these years, with the team from TMC and IIT Kharagpur team, I think this has come out very well. But now, for me, this is just a starting point, because we now need to make sure that we are able to work with everybody and build this up into a much larger, federated, distributed, collaborative system. Dr. Agarwal is here, Balachandar is here. I would request that we take up a massive scale project to initiate this, and within a year or two, make it such a large repository that this will benefit education, this will benefit treatment, this will benefit creation of lower cost treatment through this sort of mechanisms. But we also need, while we take this forward, I would suggest that we go back to the drawing board for the next generation database. The next generation database is going to be augmented reality database. How are we going to create a virtual reality, augmented reality database, which is going to become futuristic? How can we create medical databases using annotated augmented reality? We are now the first in India to do this. When can we become the first in the world to do something? So this is my request, that we now work together with CMC. Vellore is here. I remember my long stays in CMC Vellore. And I would request that the TMC team, the IIT Kharagpur team, sets up a working group to create a concept paper for how to take CHAVI to a national and international scale, where we bring in all partners and collaborators, and we can talk to the government, talk to SERB to find out what is the minimal funding and other requirements for us to take it up. And the other thing that I will request is that we go back to the drawing board to create another proof of concept for what is going to come 5 years from now. So parallelly, let us try and do these two things together. And as Dr. Arun clearly mentioned, how do we ensure privacy? How do we ensure security? Once you make things public, all the flaws here will come into the fore. And therefore, this is where we really need Jayanto, PPD, and their teams' help and support. And we will get other people who are absolute, the best hackers in the world are in our campus. So, but I have a request to the medical science and technology practitioners. My request is the following. You will realize that y'all find it very easy and exciting to learn computer science and latest tools, software, technology, etc. I understand that that subject is easier than medical science and technology, but I would like to bring to your notice that that has been possible because computer scientists have released tools, technologies, software, how to use everything in the public domain again and again and again. So today you can just take a few, if you know nothing, you can take a few blocks and connect them and make something. Tomorrow, if you know a little bit of programming, you can go down and tweak the code. All open source, all publicly available. May I request that the third thing I request is, please make medical science and technology open source so that people really know what it is instead of going only to Google Baba. With this, I would like to express my grateful thanks to Dr. Mamin Chandi. You know, when you meet with a person who you discuss anything, he said that I agreed to everything. You know, the quietness with which he proposes something and the confidence with which he says that I think y'all can do it, you have no other option but to say yes. Thank you, Dr. Chandi. We are very happy and grateful and very enriching collaboration with TMH, Tata Medical Center, Vellore, IIT Kharagpur, and others. I hope that this will spawn up into a much bigger thing. Thank you very much.
Thank you very much, sir. Yes, indeed, we have collaborators from across the country who've joined us virtually as well as joined us physically over here. We've got the All India Institute of Medical Science. We've got Tata Memorial Hospital, Mumbai. We've got the Director of ACTREC joining us virtually. We've got CMC Vellore. Dr. Selvaman was telling me he started at 1 a.m. this morning to reach us. I mean, this is the commitment to the collaboration for CHAVI. We also have certain international collaborators, and they're very interested. And when we wrote to them about the commissioning of CHAVI, they had sent us very short messages. One from the University of Cambridge by Dr. Raj Jena. So, and that will be followed by another message from the University of Cardiff by Mr. Emiliano Spezzi, Professor Emiliano Spezzi. So we will share those messages with you now. Dr.
Hello,
Jena.
my name is Raj Jena, and I head up a data science and machine learning team for radiotherapy here in Cambridge. As part of an ongoing collaboration between the University of Cambridge and Tata Memorial Centre, I got to hear about the launch of CHAVI, an exciting new image and clinical data repository for radiation therapy. I really appreciate the value of open data repositories in the data science and machine learning community. I've observed that these repositories allow the brightest minds who work on cutting-edge machine learning, radiomics, and genomics algorithms to access a body of task-appropriate clinical data quickly and without spending months on data governance issues. This means that machine learning researchers might be more inclined to work on problems and build new tools and solutions that we can apply in radiation therapy research. I also appreciate the FAIR principles of data interoperability, namely that data should be findable, accessible, interoperable, and reusable. And I think that if we are ever going to think very big and achieve international large-scale data federation programs in radiotherapy research, then having data that fits to the FAIR principles is absolutely essential. We have all observed examples of bright researchers developing novel data science and machine learning algorithms that have been trained and internally cross-validated on data from a single institution. We see very encouraging results, knowing full well that these results are unlikely to scale in the real world, and that it is so important to assess algorithms from time to time on a completely different patient population by going transnationally and assessing your algorithms on a completely different data set. It's only when this type of algorithm assessment has been performed that we can get a better idea for the robustness of an algorithm for use in all manner of healthcare settings, but also to understand and evaluate any inherent bias that might be present in the original algorithm and its training data set. And these are things that we would be able to do more easily when CHAVI exists, because as we know, many of the existing open data repositories are based either in the US or Europe, and it's very difficult to get that increased ethnic variety in data. So what do I like about CHAVI? Well, I like that it's built on modern software engineering principles, web front ends, using, for example, the use of JSON formats, which are human readable, which will reduce errors downstream when correlating image with clinical data. I also like the fact that it has a robust mechanism for archiving of DICOM and DICOM-RT extensions used in radiotherapy, but this is combined with a sensible data model for correlation with important clinical parameters. Again, time and again, our experience of such repositories is that ingesting imaging data is quite easy, but ingesting and harmonizing the relevant categoric clinical data from an electronic healthcare record can be really very hard. And it's nice to see that CHAVI has some pragmatic features on offer that will really help with this. So what are my hopes for CHAVI? Well, I hope that the project from kickoff gains pace really very quickly and that the data volume increases rapidly with time. If that happens, then I think there's a chance that CHAVI could become a go-to repository for radiotherapy images and associated clinical data that could be used and adopted by the data science and machine learning researchers of tomorrow. It would be absolutely wonderful to see that happen, and I'd be very keen to support it as much as possible in that goal. And for that reason, I wish you all the very best for the launch of the CHAVI project.
Professor Joy and colleagues from the Medical Data Center in Kolkata. Greetings from the UK and from Wales. It is a real pleasure for me to send you this message for the inauguration of the CHAVI Image Bank that you have developed in collaboration with the Indian Institute of Technology, Kharagpur. Modern radiation oncology is characterized by the need to handle large and diverse data sets across a range of domains, from digital imaging and pathology to genomics, while incorporating treatment and clinical data and other individual patient information. We know that the development of predictive models linking outcome data such as survival and toxicity to individual patient characteristics is often limited by training cohorts that are too small or unrepresentative of the general population, lack of sufficient outcome events, poor data heterogeneity. In this last case in particular, models built on small data sets are likely to fail outside of this treatment scenario because they have poor precision beyond the range of their training data. This is why the availability of image banks like CHAVI, that is open and internationally available, represents an exciting opportunity to produce advancement in the field and to support future collaborative research across the world. We share with you several key research objectives and approaches. In the radiation oncology data landscape, we are now operational with CARIFCAT, the computer-aided diagnostic research database and infrastructure that we've built with our colleagues at Berlin Cancer Center. We are making CARIFCAT the heart of our research on federated learning in radiation oncology and the reference example for our new trusted research environment. In the image analysis landscape, we have built a state-of-the-art radiomics package called SPARC that allows high throughput extraction of quantitative information from medical imaging modalities. SPARC radiomics software is compliant with the Image Biomarker Standardization Institute, of which my team at Cardiff University is co-member. In the training arena, we are launching an interdisciplinary doctoral training hub in precision oncology, unifying biomedical imaging, pathology, and genomics. This is a joint initiative of the School of Engineering, Computer Science, and Medicine here at Cardiff University, and will offer opportunities for several postgraduate research students to join our cancer research community. I understand what it takes to develop the skills needed to handle omics, imaging, and clinical phenotyping data. This kind of work represents substantial challenges and demands advanced research skills and a strong interdisciplinary approach. So many congratulations for building CHAVI, India's first oncology image bank. I wish you all the best with the launch of the platform, and I look forward to the opportunity of collaborating with you, your team, and many other collaborators around the world to scale up this approach together to drive innovation and improve medical decision-making. Have a wonderful launch event. Goodbye.
Thank you very much. We would now request our director, Dr. P. Arun, to please press the button and officially inaugurate CHAVI, the image bank.
Do you want to bring Professor Jayanta to join me?
Can the IIT colleagues, sir, come? Sir, Ashok. Please. Hey, PPD কোথায়? PPD signature টা না হলে হতোই না।
So any collaborative work is not done by an individual. So that's why we wanted you here up on stage.
রিম্পা রিম্পা কোথায় চলে এসো ওই শান্তম শান্তম আয় এদিকে আয়
Okay, with your
just one second. Ma'am and sir, please come. Yes, sir. Thank you very much.
Thank you.
Thank you, sir. It goes to you.
Thank you. That brings us to the end of this first session, and we are now going to take you to what this CHAVI is about. The demonstration or the technical development of CHAVI was possible because we had the brains of PPD, Professor Mukherjee, and the experts from IIT Kharagpur. But believe you me, there were two people from Tata Medical Center who really understands computational skills, computer languages, much better than most doctors that I've met. One of them is Dr. Indranil Malik, and the second one is Dr. Shantam Chakravarti. I think if they were not here, this project would have been at least delayed by considerable time, because to understand the language they talk about is something that we would have taken a long time. So may I please invite Professor Jayanta Mukhopadhyay from IIT Kharagpur first, to talk us about the technical development of CHAVI from his perspective. And that will be followed by a demonstration by Dr. Shantam Chakravarti from our own Tata Medical Center, who is going to talk to us about how CHAVI works. Join to that.
That's right. So, very good morning, and once again, it's my privilege and honor to be here, and particularly it's a very enjoyable experience to work with our research collaborators of Tata Medical Center, Sanjay, Indranil, Shantam, Rimpa, Tapesh, Dr. Shomin Rai, Dr. Moses. So we are working for a long, and CHAVI is one of the outcome of this collaboration. So let me give you briefly its overview. Actually, I should say that as it is already mentioned, that it is the first radio oncology imaging data bank in our country. But I would also say that it has certain unique features, which is also is a very unique and first in the world also. So one of the uniqueness in this system, from the very beginning, we have considered that we have made it very systematic, so that the system should be designed where the de-identification and the data bank, data storage, data archival, it goes hands in hand. So in view of that, the system has been designed. So as you can see that there are two particular modules in the CHAVI system. One of the part is called de-identification system, which is a kind of isolated system, and the concept is that it would reside in the premises of the hospital where the confidential data is there. So first you de-identify it. It is physically isolated to any of the network. You can have that protocol, and then you take the de-identified media by some by some hardware media. So even we are not believing the internet or not network connection, so that those data is transferred to the CHAVI data bank. It is uploaded. So this is a concept. Of course, there are various ways of implementing this protocol is there. Now, I would just briefly go through the de-identification part. Now, these are the kind of features we have incorporated in the de-identification system. It is in compliance with the international standard of de-identifications, the HIPAA de-identification standard. And as I mentioned, that it is physically isolated from the data bank. It has a private database for references. That is another very important feature. So, if you would like to really, once again, build up the correspondences with your research outcome to actual and very, the authorized persons, authorized scientists who are able to do that. So this data bank, this de-identification system has those references because it is in your premise where the de-identification is taking place. So we are keeping those references to the authorized part. So this feature is there, but those are stored in an encrypted form. So it is not very easy to get them. There is a process, only certain process, not every user can do it, by which this is possible. Then other part is that it is study-oriented de-identification. So de-identification is not just merely identifying a few items to de-identify, but in the context of your problem or study, you need to identify some of the information which are very much relevant and which you just simply cannot forego. But you have to you should put that information in such a way that the person or should not be identified by those information. So we have considered those things also so depending upon study and depending upon the nature of different as a variability of information that is required, that is flexibly you can define. You can have a metadata definition in the de-identification system, and which goes hand in hand with our CHAVI data bank data definition. So the advantage is that you directly, whatever the de-identification system is producing,
it directly gets into the CHAVI database. And there is no other manual way of uploading. Only thing is that de-identified data should be uploaded. That is the process. So it also ensures, kind of very strict adherence to your protocol. So there should not be any kind of manual error. And then the other advantage is that it's a batch processing. So you can do it in one go for many records. And also it is incremental. That is very elegant and very convenient to use, because you don't bother in which sequence a patient's data comes, because you know that de-identification is not just a one-time job. It's a study. It goes with the time. At different stages of time, you require the patient's data, because suppose you have a prospective study. So that data is going to come to you, and then you need to de-identify, you need to put your study, those data in your data bank. So it has all those references. Since we maintain these databases, it has all those references, and incrementally we can do that. So we have taken that thing. It preserves a referential integrity. It's not coming the full thing, but it preserves the referential integrity and also temporal relationships. So it's very important, because that any study has so many different kinds of images, and then the de-identification part also should maintain those integrity. Otherwise, you do not know that which image belongs to which de-identified patient's data. So that is the referential part. So you have resolved that part, and temporal part is also in the same way. So these two, that means temporal is that consistency should be there. Suppose there is a gap of 6 months of a treatment, so the same gap should be maintained in your de-identified. Even the dates should be in such a way that it should not be able to decipher from the date information itself the patient's identity from a database. So there are certain protocol we have followed by which randomly there is certain kind of randomizations of dates, but we maintain the temporal relationships. So these are certain things we feel they are very unique. And so just for the technical point, I will just quickly go through some of the things we did. Like we replaced, these are very conventional normal things, that we replaced some of the tags and we processed them. And referential integrity, I just mentioned that because we have these references, we have identified that which are the reference points, and corresponding the de-identified pieces of rows identities, they are also propagated across the various images. Then for longitudinal temporal data, as I mentioned, that the certain randomness is provided, is inserted into the time and date, so that from your database, using by just looking at those time and date, there are various secondary ways by which you can get the identity of a patient. So those are not possible because of this. So we try to do that thing. And there is a specific workflow, and we have a publication out of it, which actually describes all these technical features there. The other aspect I mentioned, it is a study-oriented de-identification. So we have created an ontology for de-identification. So we have used an ontology, and based on that ontology, you understand that how the medical doctors they are involved, and why Sanjay said that Shantam, Indranil, and how they have contributed greatly in its development. So this ontology has been basically everything came from there. The challenges and issues, also the ontology from them. So there are certain in the de-identification also we have different kinds of administrative input at job, like user management, project management. Those features are there. This is just one example, just to validate that. Suppose we have an original study, and just to show you using your, I think, treatment planning system, where you see the images and even the de-identified patient's data. If you see, then you will see largely they are just matching. Only that patient's identity would not be revealed. So it contains. So our objective is that it should contain all the critical information which is required for research or study. That should be there. Some of the limitations also I should mention at this stage, which we need to take care or in future. First thing is that it is not handling any text in burnt out pixels or voxels in DICOM images. So we assume that the images which are going through this process, nothing is written textually there. It is everything is a DICOM metadata form. I mean, not burnt out with text data on the image frames. And another part is also very very critical. And now that people are getting more and more, using more and more computational systems, and they can recover information in various tricks. So the anatomical biometry-based information leakage, that is possible. Suppose you have an MRI image, so you have the 3D anatomical structure of your face. Then you can recover the face. I mean, there are computational, there are software now using deep learning systems. In fact, they will give you some almost the identity of it. It is possible, though it requires a lot of high-tech computations and other things, research, but it is possible. Now, it is a kind of open question. So how do you distort the anatomy and preserve still I think Shantam has some ideas he was telling, but right now really we do not have any clue, and we are not really going to consider that. That part we have not considered. Now, let me quickly go through the features of medical image data bank. Here also I should say that uniqueness. You see that the identification system has some of this uniqueness. In medical image data bank, one of the most unique part, like TCIA is a very well database, diversified database, and federated data sets. People have contributed. But in our, the thing is there that whatever data has been given as a study, you can just download them and use them for your research. But in your medical imaging data bank, we have a backend database. So you can create your own data by giving query for your research. So which means you can design your data set. So that is the most flexible part. Apart from, of course, there are different studies by which these data are being populated. So as we do for the other databases, you can get all the data for the study. So this is the most advantages or uniqueness. And no, this is a system I have already mentioned. So some of the features of our imaging data bank, first thing, it is a multi-tiered architecture where the security is it preserves the it has improved security. It's an open source platform. It has because that is what Professor Pathapatim Chakraborty was saying, that computational our community, we are really geared up to contribute so that even the software tools, those are used by others, so that reinvention of wheel is not there. So since all these open source things are there, it has become easy for us to develop this system. Similarly, we also want to contribute something. If you do something in open source, again, you can contribute to the open source community, and you can make this system also available to them. So we are in the process, we are discussing, etc. But we have that advantage here also. Then the flexible queries, as I mentioned, project-wise data set, then construct any customized study-specific data set, ensuring anonymity of medical records, because I mentioned that as a protocol-wise, only de-identified data sets are going to be accepted. So if your de-identification system is strong, then you know that so it all depends upon your de-identification system's performance. So that there you have to very critically design the things. It is multi-tenant, so this CHAVI system also can host other institutes imaging data bank independently. They can get access of them, so they are independent, but of course the same database would be used, but it is multi-tenant. It is scalable because we have used this container-based technology where you have improved the tech scalability. The user roles, we have identified 3 user roles. One is administrator, then data provider, and data viewers. So by their name, you understand. So these are the 3 simple roles are there. Some of the data bank schema design, I did not go through, but all these things, the schema, etc., we designed mostly, in collaborations, or rather, I should say, the guidance from our TMC colleagues, Shantam, Indranil, Sanjay, Rimpa, all of them have contributed to this. So this is the kind of ER diagram. I was mentioning about the tiered architecture. So this is the way the information access takes place in this system, because it has improved security feature. So there are certain things. So those are technical things which can be taken care of by this. Now, presently, we have 4 studies whose data have been uploaded, and still it is ongoing because many other image data and image and clinical data. So both image and clinical data, they are uploaded there. So we have Radglioa, and these are the numbers. Numbers are very meager, we understand. I just started, so we hope that it would have more and more number of patients and also more and more studies. And as wished, as Professor Dr. Rodu, Dr. Chandi, and Professor Parthaputim Chakraborty, all of them has wished that this data bank and our foreign experts who have also commented, we also expect that CHAVI data bank would be used by the greater community. And this is a slide I am like to, but Sanjay has already shown it. Actually, this is a dream that has driven this project. And it's a very fraction of it presently what we are having today. But if we see the overall picture that we want digital pathology, we want many other things into our database, not only the radio oncology. So those things are possible. Of course, this database is very much targeted for radio oncology. That was our focus, but no, we would be able to again diversify it in various other domains. So with this, once again, let me thank all of you here who are here listening to this, and my collaborators in Tata Medical Center for their very enthusiastic, I should say, and also very knowledgeable participation. I must tell that I was discussing that how busy how busy our doctors are, and we have interacted physicians at various forums. Personally, I have some experience on that, but I can vouch that one of the most satisfying interactions I have for a long with them, because they give time, and it is very difficult. It is very precious. Time is for them, I understand. So again, thanks to them. Thank you very much.
Video. Yeah, so good morning. I am Shantam Chakraborty, and today I have with me my colleague Surajit Kundu, who will be taking us through this demonstration. I will be taking care of the first part, which is how we designed the database and the de-identification system in a demonstration. So as I'd mentioned, as Sir had already mentioned, we have a huge challenge when we are de-identifying clinical data along with DICOM data. And our focus from the start was to ensure that there would be flexible storage of clinical data at scale, ensure that hierarchical relationships between the data is maintained, and facilitate queries across the image set. Now, this is just a pictogram to show how patients are. So a patient is not static. A patient, particularly a cancer patient, can have a diagnosis that comes on one day. What we are representing by stage is what is the state of the disease. So our database entity relationship diagram actually reflects this natural progression, or as we like to call it, the natural history of disease. So our motivation was to ensure that people can keep on storing data of the same patient longitudinally over and over a period of time and ensure that the entire data is available. The next challenge we had to solve when we were doing de-identification was harmonization. And this is a big challenge because, as we know, the same clinical data, as basic as age, can be recorded in various coding conventions, various measurement scales, and various units. So how did we do that? So let's start with the DDiS demonstration. So this, we are showing a real live patient. This is not a patient, this is actually a random phantom image. And we have specifically taken a cone beam CT image to show how this is being exported. Approved plans will be exported from the treatment planning system or a PACS system as DICOM data. And because this is being done from Eclipse, it also has the dose information and the plan information, which is sent along with the patient. The data after export can be stored in any one of the network drives or local storage networks as per your desire. And this will completely depend upon the network that you have in your hospital. So we are flexible enough to accommodate this. So here I have created a folder called test, and then we just click on export selection to export the data. Once the export process is completed, you would see that there are 67 total items. These 67 items comprise of DICOM images, which are available as DCM files. In addition to that, they will comprise of structure set files, dose files, and plan files. Now, one of the most important things is that we actually de-identify the entire gamut of radiation oncology DICOM extensions, which means we de-identify the structure set, we identify the dose, we de-identify the plan and the registration objects also, thereby ensuring that data is maintained for future use in extensive treatment planning systems, for example. Now we are preparing the DICOM data for de-identification. The first process involves taking all the files and converting it into a compressed folder. This is currently necessary for the de-identification system to work, but maybe in future iterations, we can also have more flexible ways of uploading the file. As Sir had mentioned, the de-identification system has an authentication layer. So every person who does the de-identification needs to log in. The system maintains a log of the activities that are performed. So after logging in, what the user will have to do is they have to start the de-identification process. And this starts by selecting the file, which we had already converted into a compressed archive. And it is important over here that in addition to this DICOM data, we also set up the site where this image is, the site information, and the type of image. This is important because it allows you to query across image types. So you can, for example, query for cone beam CTs or verification images of a particular diagnosis in your database. Once this is done, the pre-processing step involves keeping all the images in a particular order and ensuring that the UIDs are de-identified appropriately. This is actually real-time de-identification that is happening without any change in the video speed. And depending upon your DICOM dataset size, this is a cone beam CT where the image matrix is of the size of 384 by 384. The time taken ranges anywhere between 20 seconds to few minutes. Once this is done, the DICOM data actually can be saved into your local file. And this is again available as a folder. What is very important to understand is that during the de-identification process, the system will itself create folders for each image series. So although we have zipped all the files together, they will automatically get segregated into separate folders. So this is what the folder architecture will look like. And you can see the folder is represented by the de-identified DICOM data. And this, if you look down, you will see now there is a JSON file. This is the key to ensuring that only de-identified data goes inside the DICOM database. This JSON file contains the information that we have, and without the JSON file, the system will not accept the data inside the CHAVI data bank. So you can't just randomly push any DICOM dataset inside it. Here, we are just showing how these metadata has been de-identified. This is, of course, a copy of the data. And you can see that the dates have been de-identified. Please pay close attention to one of the dates, that's 2015, April, March, because we'll come to this date again. You can see that we are retaining information on the DICOM tags, particularly the imager energies, current, etc. This is important, and this is actually stored in the database also separately because it allows you to query this information for radiomics research. As we all know in radiomics research, the image acquisition plays a huge role. So you can actually query for quality parameters. Now this is a demonstration of the same patient. We de-identified, we brought it back into the treatment planning system. And at the same slice level, you can see that the dose matrix remains the same. There is no change in the monitor units or the field size, which means that information is also preserved. And you can see even the intensity information has not changed, which means the image is actually available for your future analysis. Now, after this, let's look at how we approached EHR de-identification. Now here I would just like to pause the video for some time and essentially tell you that EHR de-identification is complex because data comes in various manners. You have tabular data of various field conventions, various field types. How do you harmonize this inside the database? So you may have a database which accepts age in a particular format, but to harmonize this in a manner which is reproducible for the study, currently what we are recommending is use of a REDCap database. And we can assist the people to use the REDCap database that we have in Tata Medical Center for this purpose, such that data exports in the future from the database will be automatically harmonized. So let's start the video once more. So you start by selecting the EHR data. And once you start by selecting the EHR data, you get can you start the video, please? Okay. So probably something, just let me pull it forward. Yeah. So you can see that we have just put this test data set from REDCap, and it is running on the de-identification system. It just takes a few minutes to few seconds, depending on the volume of clinical data that you have. And now we will just take this JSON file, which will be generated. Again, this is a JSON file. And one of the advantages of JSON files is these are both computer and human readable. So this is very useful. And this is the view of the de-identified data set vis-a-vis the original data set. So you can see the age is maintained, gender is maintained. The dates have been de-identified while ensuring the difference between them remains consistent. So this minus 35 days is the difference between all of these dates. These dates, therefore, will allow you to do an actual survival analysis. So that's very important. So this is retained with respect to the patient's date of birth. And therefore, once the DICOM data is de-identified, you actually get to retain the whole thing. You, of course, have the pathology information, which is de-identified. This also is actually harmonized in the database using lookup tables. I would also like to draw your attention over here on the site. So you can see the database actually records this as central nervous system, but the system records this as brain. So this is very important for harmonization. Please take a look at the DICOM date difference also. It is same, which means your DICOM information on the patient's natural history timeline is being maintained. So this actually allows you to go back and query the natural history of the patient in its entirety at some time in the future. You always, also we will just show you at the bottom end, there was a small portion that, let me go back there. Yeah, so you can see that the radiation start date and end date is an example of an event which has happened over a period of time. We maintain the integrity of the duration. So it is 45 days difference between start and end. The same difference is there in the de-identified data. So now Surajit will take us through how to upload and download data in the repository.
A very good morning to everyone. So today I'll be presenting the features and the functionalities of the medical image data bank. So this CHAVI is a web-based multi-tier image data bank. It has a role-based access control, and the data are saved in a relational database. And we have a query interface for searching the dataset based on multiple queries. And we have also modeled the project-wise data in our CHAVI data bank. So in our role, we have three roles: data provider, data viewer, and the administrator. Now, the CHAVI system is hosted on the cloud with a domain name of chavi.ai. So anyone can access this having an internet-enabled device and through browser. So now we'll go to the repository and we'll log in into the system as a data provider. And we'll understand how the data can be uploaded to the system. So once we go into the system, we can see there is a section on the top of the page where we can upload a study of a patient. So by clicking this section, I'll select a folder from there which contains the study of a specific patient. So once I'll click, I can see there are 68 files which will be uploaded to the system, which is enlisted here. So by clicking on the upload button, I'll upload this file. So once I have uploaded, I can see the images. So now if you want to visualize those images, we have also integrated one DICOM viewer. So as we can see in a series, there are 64 slices. So once I'll click on this, I can see the images, and also at the right, I can see the metadata. The patient identifiable information is de-identified and replaced with has value. And the other things like the date and the record information of the metadata that is there. So that can be used for the radiomics research and can be used as a feature. So apart from this, we have also integrated one magnifying tool which can be used to clearly visualize a part of the images. And this magnifying tools, this zoom out, we can be done by different scale. The default is 3x zoom. So now I will log out from here and I will log in as a data viewer and will show that how the data can be queried from the interface and that can be downloaded. So once I log in into the system, I can see the profile based information of the users. So for searching any DICOM, I'll click on search DICOM option. And here I can see the query can be done by study date range and birth of the year range by the diagnosis site, image modality, and the available treatment. Now we have a total of 5 projects, including general study. So if we want to see the patient's data set, by selecting a particular project, we can see here we have more than 100 patients data of Radcliffe High project. And this data set can be downloaded by clicking on download images button. So after that, the images will be compressed in a zip format and will be downloaded to the user's system. We have, apart from this project, we have also has the Intel Hub project where we have around 50 patients data. And in Lang also, we have around 50 patients data, and that can be downloaded. We can see the studies of a patient. So now, if I want to browse a DICOM data from our query interface, so suppose I'm going to search a data set belongs to breast cancer. So I'll select the diagnosis site and search. So by searching, I can see the results here. So we have also shown a modality wise distribution there and summarize the number of patients, number of studies. And the images can be downloaded by selecting the particular study. And also individual studies can be downloaded. So now if I want to search the cancer patients of CNS model diagnosis, so I can see. So this will take some time based on the data, it will come up here. So as I can see, there are 108 patients, sorry, 109 patients and having 426 study. Now I will show another diagnosis sites results. Here we have around 9 patients, I think, 16 patients. Now we also can search our data set by the image modality. So here I'm searching on by PET modality. Now I will show once we download the data set, how does it look? So once the results come up on the page, we'll select a particular study from here. So here we have selected that particular study we have already demonstrated. So by clicking on this download button, we can download the data in zip format. Now we'll extract this file and we'll have a look on this data. Here we can see the clinical data of the patient. And the de-identified medical images. It's including the one RT structure file, one RT dose, and one RT plan file. Here we have shown the anatomic site-wise distribution, how many number of patients data we have uploaded. Now we'll log in as a admin and we'll show there is primarily 3 features like center management, user management, and project management. We can see there is only one center currently. So another center can be added to the system, can collaborate for adding the new dataset. And also we have a user management system where the administrator can register new user of different load and can also modify the existing data. We can see there is currently 5 projects. So new project can be created through the system and the data can be entered. Thank you.
Thank you, Surajit. Can we have the last video, please? This will be a quick one. We will just quickly take you to the functionalities that are available on our CHAVI website. So in the CHAVI website, the first thing that we have done is provide you with a contributors page, which gives you details of how you can contribute. We require users to register on our website, and they can register, as we have mentioned, as a data viewer or as a data provider. In order to register, there is a register for the CHAVI repository web form. It is a simple form which involves you to provide your identifying information in the form of your name, email address, institute address, and your country of origin. Currently, we are just collecting this data for aggregation and for our internal records. If you are a data viewer, you would be asked a question as to which project you want this data to be used in. Now, this is not a required field, but we would like to have this information for collaborators, again, for extending CHAVI in the future. It is too important to remember that CHAVI, once this is done, this doesn't automatically give you access to the repository. It has to be vetted by a group of people, and these people will provide you with the access credentials. We also have the data dictionary available on the website. Why this we have put on the website is because as we have currently, our interface for querying is quite limited. But these fields are actually available, and if data is available in the clinical study for these people, we can construct queries for you for downloading this data. This is something that we are planning to come up in the near future. We are planning to have all data sets come up with dataset articles, which will receive a digital object identifier and will be citable. This will ensure that our contributors get the attribution they deserve. Thank you once again for your attention.
Thank you, Shantam and Surajit. We will move on to the next speaker. It's Professor Parthapratim Das from IIT Kharagpur. Professor Das is someone who we've collaborated for more than a decade. He's obviously an expert in his field of computer sciences and AI. But the best part about him is, the accessibility and the approachability. As a computer science expert, he's always available, and he would listen and answer your queries and take a problem to its stage of solution. Professor Das, CHAVI and the big picture in the technical research in oncology, please.
Good morning, So we have really understood about what is CHAVI as a image data bank. So in my brief comment note here, I just wanted to, look beyond that. If we have a data bank, as of course, as medical practitioners, you all appreciate, you all know how to, what is the importance of data and what can it give uh, in terms of research, in terms of treatment, as well as in terms of predictions. Uh, what I wanted to look at is take you through the fact that the whole lot of opportunities that opens up when we have access to such data banks by the use of artificial intelligence. I mean, there are different names. Those names are the different terms. Those terms are related, but have different shades a little bit. So what I would like to take you through over the next couple of minutes is glimpses of what direction the cancer research is moving with the use of a variety of AI and machine learning techniques. So just to probably most of you are familiar with what is AI, what is machine learning, what is deep learning, and so on. But I just make a few comments to make sure that we have a clarity baseline on these terms. So by machine learning, which is become so common in use, the basic approach is to design algorithms based on data that the algorithms have been trained on. So you have a data set, you know the outcomes on those data set, and using different techniques, you train the algorithm using that data set, so that what you get is very significant, that you can perform tasks without explicit programming. That's how it becomes different from the traditional computer science that we have been doing, that, well, this is the logic, this is how to go about, and you write a program to do that. But machine learning is empowering us to discover those algorithms which probably we don't even know, even when they work, we do not know how they work, why they work, or if at all they work. So machine learning has primarily taken two approaches. One is supervised, when you know your data, you have annotated your data, so you know the input and output, and you are building a model based on that. So it could be a regression model, which is basically computing the different kinds of input-output relationships through an automated manner. You may want to do recognition, classification, and all that. And the other approach is where you have unsupervised algorithms, which talk primarily with data that have not been annotated. So that's a bigger challenge, but that also has a lot of applications in reducing your dimensionality. You may have had 30 features, but are really all those 30 features relevant, or you could do with 5 key features to actually go through the analysis. So particularly in terms of machine learning, what over research became important are the artificial neural networks, which are basically inspired by human neurobiology and has multiple layers. What is important to look at is a network at the bottom. On the left, you have an input layer, which is amenable to the kind of input that you can make available to the algorithm. And then the rightmost layer is how the algorithm gets back to you. But what lies in between, the hidden layers, is the knowledge. And that knowledge is getting generated. That's the opportunity that we have. And we can see the kind of exploitation of this deep learning methods that have happened over the last more than a decade. And I would just point to you to the period, say, from 2013 to 2017. You can see the exponential growth in this area. And that's the opportunity that systems like CHAVI can really exploit. So talking about some of the specific tasks, the big role that AI can play is in terms of handling cancer images. So the simplest thing is to understand the images better. So where I say that better eyes, by a particular deep learning model known as convolutional neural network, which is kind of become synonymous with research in this area. And using that, actually in different other fields, you already have proven results like driverless vehicle, face recognition, or say mobile check deposits and so on. A lot of similar stuff can happen in terms of the cancer imaging. On the right are some of the publications that have happened with various kinds of AI application in imaging. Clinical photographs are being regularly used, like skin cancer, like detection of lesion of clinical importance in polyps during oncology. These, I have not put the detailed references, but each one of them actually are a result of a couple of publications from different groups which have shown that these are the possibilities. Radiographic imaging is another area where there's a huge application of deep learning happening with lung module detection and classification, lung cancer screening. And in many cases, what's encouraging is actually the deep learned models match or even at times outperforms the prediction given by the known experts. They have a high sensitivity and specificity and successful in segmenting tumor volumes. Radiotherapy treatment planning is one of the areas in which we ourselves have used CHAVI in different contexts. There are several such in terms of radiographic imaging, detection of anatomic features from malignancies, prediction response to treatment, and so on and so forth. The other area where this has really been proving very powerful is digital pathology. I mean, a significant part of progress in digital pathology is riding on the deep learning methods like diagnosing breast cancer metastasis in lymph nodes or automated Gleason grading of prostate and so on. So these are the different opportunities with cancer imaging that we can leverage as we build up more on the CHAVI side. Of course, there are related information, like CHAVI talks about some of that in terms of EHR. Santam was explaining earlier, and a lot of inferencing can directly happen on those. There is a lot of research that is going into cancer treatment toxicity. Some of the specific studies are what's given at the bottom. So these all also become the consequent possibilities. Not all of them significantly only use imaging data. They use other related data as well, but the approaches are important. It's finding a lot of use in translation and oncology, discovering models of different protein structure, drug interaction structure, drug development, repurposing, and finally, last but not the least, the clinical decision making. This part still is in kind of infancy, I would say. I was looking at, but not many proven, proven reports. There are attempts, and naturally there are a lot of questions around this, but the opportunities are severe. So before I close, I would like to highlight what is important to take this field forward is to identify the limitations and future directions. There are few very deep limitations. The first being is what we say is the overfitting problem. You are learning the whole thing from a set of data, annotated with the understanding that you have. Now, can you apply it to a different context? If you are doing that, is it generalizable? So this generalizability problem, the real world application, is still a big challenge, not only in the medical context, it is in general in the context of deep learning. Obviously, a second challenge is in terms of data access and equity, in terms of limitations of data access restriction. DL requires a large volume of data. So you have several disease prevalences which do not have that much of data or that much of known annotable data. So it cannot be applied there. It is siloed through individual institutions. There are different factors in data rot that happens. A very significant philosophical question, which has several practical and legal implication, is whenever you do a kind of medical diagnosis or prescription, you must be able to evidence it with reasons as to why you did that. Why was the protocol followed and so on. In terms of deep learning, the main difficulty is, as I showed, that you know the input layer, you know the output layer. In between, what's going on is known to the data. So you know what the outcome is. Maybe the outcome is proving to be correct in 90% of the cases, more than what human beings are being able to do. But you cannot explain why it is happening. So that becomes a major challenge, and it's known as the black box problem, on which several research is going on, including what PPC and his teams do, is in terms of explainable AI. You have an outcome. Can you explain why that outcome happened? So that is very important. And certainly, last but not the least, there needs to be a lot of education and build-up of cross expertise. Like PPC said, that we are very weak with the technologies, are very weak in learning medical science. Doctors are doing somewhat better in terms of learning computer science. So there needs to be programs which are collaborative, joint in both these areas, and we need a joint team in terms of doing this. So how CHAVI contributes in this context is in terms of the different features with Professor Jayanto Mukhopadhyay and Dr. Santam has already mentioned. Robust de-identification, which provides privacy protection, ability to store any kind of DICOM image, interoperable. Actually, I missed one part, that on the output side, it is using JSON, which is significantly interoperable. Temporal imaging, integration of imaging annotations, heterogeneity, it's findable, accessible, streamlined data capture, it is open, scalable, multidimensional, and so on. And therefore, CHAVI as such not only is an Indian contribution on Indian data, but overall in terms of the architecture and the expectation, it meets all the requirements of the leading data banks in the world today. And going forward, I just talked about one side of AI in terms of cancer research. That is, if you have the data, how can you use AI to make better inferences? There's a complete another side of AI, that is, how can you use AI to build better image data banks? Some of which PPC was mentioning in terms of augmented and virtual realities that can be used. Annotations themselves can be smart in terms of deep learning. And we did a lot of work in that in terms of other domain contexts, not in medical context, but those are the things which can really scale up the entire operation. Here are some of the publications we made while building CHAVI. Here are some of these are all work jointly between Tata Medical Center and IIT Kharagpur teams. These are publications where we have used CHAVI to make actually different clinical analysis. Thank you very much. Here's a reference from where most of the research I have talked of has been picked up, so you can get the actual references of the teams and works in that. Thank you very much.
Thank you very much. This session has a few practical things that we will demonstrate. And who other than Dr. Rimpa Achari, who's been a pillar of support for the CHAVI project. The first small steps taken by our department to try and implement practical research in improving cancer care. Dr. Achari.
Yeah, I would begin by saying a very loud thank you from all of us to all of you who are with us this morning. And what I will do for the next 5 to 6 minutes or so is take you through our project's moments in CHAVI. And the stage is quite set with the architecture for these projects to take on. So like you have seen, our very first, we touched base on commonality, and we said we must be together pandemic irrespective. And we have to find a common language between our engineering partners and us as physicians, like you've heard in the morning. And who better than like Sanjoy and Indranil, who are no less engineers, to take us through. And we could establish a language of common communication with our experts from IIT Kharagpur, from SMST Kharagpur, and all of you are here with us this morning. So the buzz after those initial discussions we were very clear that CHAVI would be clinically led and equally technically partnered. And the buzz were that there are common cancers and there are very difficult to treat cancers. So we were trying to identify areas of need. We knew that cancers have various molecular signatures. Patients receive various kinds of treatments and have varied outcomes. I mean, what you guess may not be what you see. And therefore, that very hopeful thought of augmented reality coming in as a dimension of CHAVI excites all of us already. So how could we see beyond the visible was something that was bugging us. And we said, what is the biggest limitation in the data space? So as physicians and engineers, we decided that we must break the curse of small data sets, like Raj told us, like our partners from IIT told us, and of course, Emiliano, who's now a good friend, told us that it is the curse of small data sets. So we must scale up CHAVI to as big as possible. But what is biggest in the picture? Biggest in the picture are our patients, and all of us would agree, whether we are engineers or doctors, it is our patients who come first. And therefore, we decided that every information banked in CHAVI would be passing ethical review. For prospective studies, patient would consent. For retrospective, we would wait for waivers given by the EC before we did anything with the images. So the post-discussion plans were, we came to a common ground that medical image data analysis is essential. It is contemporary. It may hold the key to better outcomes, lesser toxicity. Any image banked would have ethical clearance. Transfer learning between organizations, between friends, colleagues, and engineers, profession irrespective, should be simple and efficient. What I tell you, you understand. What you try and communicate, I understand. Otherwise, we reach nowhere. Projects are essential to establish the workflow. Everything is theoretical till now, but we'll try and show you how we try to establish workflows through various images, pan sites, so that, we don't struggle with the image modality for a site versus no problems for another site. And that projects would be very versatile, that we must look at all subfields of machine learning, like Parthuda just told us, and we tried to do that. Most of all through CHAVI, what we developed are very beautiful relationships with our engineering partners, and we try to develop through CHAVI and through our associations with IIT Kharagpur a very different training curriculum for young radiation oncologists who now pass out from varied organizations of the country, a program called the SURAQSA. So it's a clinical oncology, a very special certificate with a project in engineering and medicine together, which is a mandatory requirement. And of course, grant hunting, nothing happens without money. So coming to our specific projects, you've seen how the CHAVI General Image Banking project was our flagship. The purpose was to initiate oncology image banking in CHAVI by providing CHAVI information to patients and bank images after their informed consent. And we can only be grateful to the community of patients and their caregivers. 500 patients more than 18 years and above gave informed consent. We are in the pipeline of developing a CHAVI junior component, and the pediatric assent forms will go into ethics committee next month, soon after Diwali. Treatments for this bank involved radiation as a component of multidisciplinary care, because we wanted to have a finger on the radiotherapy imaging bank. So what's happening to the dose plans, what's happening to the DVHs that can get reconstructed, etc. CHAVI repository was constructed, like you saw, like Shantam, Surajit, all of us, Parthuda and all demonstrated Jointuda. And we tested all imaging modalities, PET, CT, MRI. I don't really have to list it out, but all forms of imaging that involves radiation oncology treatment, planning, delivery, and verification. So we have CBCTs banked into the CHAVI, linked to patients and outcomes, all ready for you to use and generate more information so that we can benefit patients as a community. And the clinical and biological information is also banked, and the de-identification information is also banked, like you have already seen. So the projects, namely, you were hearing all acronyms till date. So we focused on head, neck, breast, lung, and brain to begin with. Head, neck, breast, common cancers, challenging cancers, lung and brain, difficult to treat cancers. And we said, so there is some problem with the formatting, but just to tell you that head, neck was testing the use of metabolic imaging to improve outcomes and adapt radiation doses for locally advanced oropharyngeal and hypopharyngeal cancers. For breast, it is a legacy of the hypo trials that Sanjoy, Shantam, and Team TMC is now generating: palliation, testing new fractionation, testing and looking at toxicity and the radiobiology of tumors, and of course, bringing down treatment times if possible. And we have partners in the HIPOT legacy from all of you who are here with us, and thank you for the same. For lung, I'll show you very quickly. We received partial funding from Imprint, and we are grateful for that. And rat glio, glioblastomas just devastate. They are incurable cancers. And the implication of a diagnosis of cancer of glioblastoma goes much beyond the patient. It's a complete devastation for the family, as well as a lot of social impact there. So those were the cancers that we chose. So there are many patients, and like we said, we are testing all sub-levels of machine learning there. Intel Hope tests PET radiomics, HIPOT adjuvant looks at dosiomics, and of course radiobiology, prediction modeling in Imprint, and core MR radiomics for high-grade gliomas of the brain. More than 2,000 images individually seen by 2 different radiation oncologists, every series segmented, annotated, cleaned, de-identified, feeds into CHAVI. The CHAVI rack is accessed by our engineering partners. They come up with predictions, they come up with molecular associations. We did a few pre-radiomics testing for brain. The ongoing research inputs gets discussed and it goes back into the loop. So, it's like nuclear fission. The more we feed, the more we learn. And that is the basic principle of CHAVI. And when there are early results, there's pure excitement. And you can see Sanjoy and Indranil are just short of getting into that laptop. And I always have fun at their expense. And so early results bring in a lot of excitement. You've seen that it's been published because we believe that what we think must undergo peer review. So projects we'll show you have undergone peer review. They've been published. After suggestions, we made corrections, and you've already seen the structure of the banks. So head and neck, it's a very privileged journal, and Sanjoy's put that in through. It will explore tumor metabolism. And we feel actually humbled by the fact and happy that every project had a Circo fellow. And the fellows learned something different than only, handling patients is very important, but to look beyond is, I think, equally important. And Saurav was our fellow who worked with Team IIT here for breast. It was absolutely spearheaded by Jointoda Ritesh, our fellow, and of course, Team TMC, and it got peer reviewed and taken through the first toxicity and the dose outcome and the quality assurance measures. And that is something that we are looking forward to. You'll soon see that. Again, Imprint went through peer review. There could be possible prediction, but again, we need to scale up the number of patients so that it is generalizable, and that what we are trying to predict is actually predictable across communities, across continents. And all of this feeds back into CHAVI. And red glio high is again glioblastoma radiomics that we are looking at. And we've structured this radiomics data set, and you can access all integrated molecular information about these brain tumor patients into our database, because 100% of our neuro-oncology patients undergo integrated molecular profiling, and all the information is available freely to you on the CHAVI data bank. Feel free. And we got the abstract through for a very recent congress in the EANO set. And of course, what is important, what we learned is through these data banks, it's also important to think laterally. So we used the same data set and did a health services research, and that got peer reviewed. So then we know that whatever molecular or decisions that we've tried to feed into CHAVI are seen by the experts in the world. Either they shoot it down, we correct, we put it back again, and that's how the cycle goes on. So let us look at our initial chart. Grant hunting, of course. And please get oriented to Professors Parthuda, Joyanthuda, and Parthuda again, because they just find grants without any benchmarked funding. And if we ever have to look for money, I mean, Sanjoy just goes to them and we try and get as much. So we are thankful to NDLI, to Government of India, to SERB and Imprint for giving us partial funding. We were able to establish the SURAQSA program, like you say, and all our fellows here, the happy looks on their faces, they are parts of these programs. Images have been banked with ethical clearance. Workflow for imaging research has been established. We have explored, we are exploring various subfields of image analysis. And like you saw, Raj and Emiliano gave their inputs, and this has been an adventure which is no less than that of Alice. So come, let's scale up CHAVI. What do we have to offer? Where do we go from here? For research, we will bank all the projects that have completed with or without funding in our department as images, ready for everyone to use, publish, learn, and do even better. CIRCO, like we said. And then, of course, we must look at something even more important or equally important is quality assurance for radiation therapy. And more of this is coming up soon. You will hear a lot about the SURAQSA project. So come on, let us move from first small steps to the first strides of CHAVI. And thank you all for a patient hearing.
Thank you, Rimpa. We've got 10 minutes for discussion, and we have people joined us from across departments over here. Are there any burning questions? Otherwise, if you don't mind, I would actually request some of you to mention about your thoughts and what are your thoughts about integrating into CHAVI? So, any questions? Yes, Jyotmaya.
Sitting. Thanks to the TMC team of CHAVI and the IIT team. What I understand, for the first time I'm participating in this kind of program related to CHAVI. What I understand that you are developing one very exhaustive imaging bank, and also you are doing research, taking the help of the medical experts and also the computational experts, and you are trying to make it open for all researchers in every relevant field. From the imaging point of view, you may consider it as a question or as a suggestion or humble submission, that if we want to make the imaging bank very exhaustive, we have to think also to develop the dimension of the relevant phantom image bank, because recently different kind of imaging phantoms in the context of different tumors, cancers, and other problems are developed to appreciate the performance of the particular imaging. That may be ultrasound, that may be CT, that may be MRI, but there the material scientists and the relevant experts keeping role to develop the synonymous situation where you can relate
in the real time what is happening when the matter energy interaction is going on. It may be for the particular material structure or maybe the tumor. So that will help us to understand or to appreciate the image appropriately, how the radiation material
Sure, sir.
interaction goes on.
I think your point is very well taken on,
So
on
that
having
may
front-end
be
image bank. Thank you.
that may be one. Another dimension I am just requesting, or my question, when you are annotating the image or in the image data bank, whether you are considering the subjectivity of the subjects or the radiotherapist or the experts when they are annotating it, the how many people or how many experts they are participating in this kind of clinical annotation.
So
So
this is mainly sort of categorical data that has been put in and some demographic data. So subjectivity is pretty limited. It's histopathological data, outcomes data. So subjectivity is pretty limited. It's all, you know, data bank that is being annotated is all verifiable. So it's less subjective.
thank you.
Thank
Thank
you.
you. Thank you.
Any other questions? Otherwise, can I just ask? You know, I've got the person who looks after Tata Translational Cancer Research Center over here, sitting at the back, very quietly and listening to all this. Dr. Shekhar Krishnan is one of the sort of experts in pediatric cancers and also the lead of our Tata Translational Cancer Research Center. Shekhar, you know, this initiative, as you can see, came up more as an enthusiasm, and we are all delighted that, you know, it's reached this far. Is there any way that you can think that TTCRC can now join in, complement, and enhance the project?
So first of all, I wanted to let me introduce myself. So my name is Shekhar Krishnan. I work at the Tata Translational Cancer Research Center. I'm a pediatric oncology physician. So I'm a pediatric. My specialize in pediatric oncology and blood disorders. So first of all, I wanted to congratulate the entire team. This is a Herculean effort, and I think I feel breathtaken by it. I mean, it's just remarkable. It conceived as an idea, and to see where it is now at this stage, it's mind-boggling. So I first want to congratulate the entire team, both the clinical team and the engineering team. This remarkable feat. This is my first comment. The second comment is that from our perspective, we are from the Tata Translational Cancer Research Center. We're using clinical data similar to this approach, clinical data with biological samples, and using high throughput molecular profiling. So I can see a synergy between the molecular profiling that is coming from tumors with the radiomic profiling that is coming from with the potential of the image bank. So I can see a lot of synergy, opportunities for synergy, and this is why I find it very exciting. So that is my sort of early comment. But more than that, I wanted to just extend my congratulations to the team. One more point I want to make is that for pediatric brain tumors, the radiomic profiling, I apologize, radiological classification of tumors closely matches molecular features, and that is one of the ways in which now we have classified one of the commonly occurring high-risk brain tumors called medulloblastoma. So I can see a great potential in this line of work.
Thanks, Shekhar. We'll reach out to you to try and see how we can complement and enhance CHAVI. Thank you so much. There are eminent people over here in the audience, and we've got someone who's not directly linked to oncology, whose name I'm pretty sure most of us have heard from the ones from east of India. Dr. Sunip Banerjee is a reputed cardiologist, and he's sort of sacrificed his busy practice time to join us. And if you remember, Sunipda was instrumental in giving ethics committee approval. He was the vice chair of the ethics committee. He gave the ethics committee approval to the CHAVI project. Sunipda, the concept of developing an image bank, especially in oncology, and where do you think that cardiologists can come in? Whether can we complement? Can the bank actually be something that you can use?
Yeah, I think I was just thinking, the moment you gave me this idea. Now, image when it goes for the cardiologist, now not limited to chest X-ray, but this is also important for serial comparison. What is important, I can tell you, because there are people who are not from our community as sitting. We have a different disease burden at the present time from heart aspect. Like they see more of unusual cancers. So we don't see, we are seeing heart attacks, we are seeing heart failure, but there are areas where the number of patients who have a atypical presentation of heart failure or heart attacks. Now, there are algorithms by European and American people developed in echocardiography, and this has a value. Now, you know, echocardiography and ultrasound is similar, accessible, it is affordable to most of the patients. My suggestion, when you ask me this question, we have lot of people with a complaint একটু চললে হাঁপিয়ে যাচ্ছি বা আর পাচ্ছি না. So there are people who think that this is due to age. Other people think it is a deconditioning effect because we are now mostly not working. We are all sedentary in our lifestyle. Whoever we are active, we academician particularly, all are sedentary until and unless we are doing a routine work. But at certain point of time, this may not be just deconditioning effect or something. So it may be a heart failure. So we can do echocardiography, and this echocardiography most of the time done by people who are not very expert. But the machines are giving all the requisites parameter to look into the filling pressure of the ventricle, whether the heart is stiff or not in nutshell. That is the. So we have various parameters. So these are things which can be utilized to keep a make a solution. So okay, if I mean, my knowledge with a limited computer and statistics goes like this, that if I have a breathing difficulty, if I have this disease in the background, and then in the echocardiography this is there, then the probability or the scoring system of heart failure goes up, and then probably we appropriately treat.
Sure. I think your point is very well taken. Even in oncology, you know, now there's so much in the use of imaging in cardiac imaging to try and predict the toxicities that we give in cancer. So basically, radiotherapy induced heart failures, drug induced heart, you know, chemotherapy induced
That's
heart failures.
definitely
So all the muga imaging, the echo imaging that we are doing, we can try and see if we can work with you to develop a structured toxicity prediction models along with our colleagues in IIT Kharagpur. Thank you so much.
Thank
Infection is high up in the list, and you know, we are all worried. We've got our masks on because we are worried about infection. Yeah. And we've got one of the pioneers of infection control in India. We're privileged to have as colleague Dr. Sanjay Bhattacharya. He's the head of our microbiology team. Sanjay is also leading the joint microbiology, molecular medical microbiology MSc PhD program with IIT Kharagpur. And my question to you, Sanjay, is microbiology is, and you know, infection-induced cancers. We know that's something that happens. Now, with CHAVI, with you diagnosing an infection, there not be further inputs that you can give with images that can help us, you know, put that into the algorithm? Is there any further suggestions, anything, any way that you can try and integrate?
Okay. Thank you, Sanjay, for the kind invitation and to be part of this enormous initiative. Now, there are many areas I was thinking where CHAVI or a CHAVI-like system could be of great use. Now, let us think that what are the areas in which the inspection or observation plays a role in clinical medicine. One of them, let's say, is rash-like illnesses. So I think you need to team up with a dermatologist where you develop a repository of image banks of various types of rashes and dermatological conditions. The second is in the field of microbiology, we use microscopy for the diagnosis of various infections. Be it the colony morphology or be it the microscopic morphology, we see it. But these are very expertise dependent. And these expertise are not available in all parts of India or all parts of the world. We also look at graphical images of real-time PCRs, of blood cultures, and sometimes these images are ambiguous, and it is the human mind which actually analyzes these images and give us an information whether they are really positive or negative. Sometimes we make an error, sometimes we are correct, sometimes we are not. So these are some of the areas in which I think CHAVI can make a difference by developing a knowledge base and an image base. And my second submission to you is that try to take CHAVI to the masses. So by that, I mean that we should develop an app or an application which is usable on mobile phones, because we need to use it to actually ameliorate the problems that we have in public health. So if you imagine a situation, a patient with a rash in a rural area, most of the people have got a mobile phone. They can upload the image and send it to the repository for analysis. The same could be done when you look at a bacterial culture. There is the human mind says whether it is E. coli or Klebsiella, but that is expertise dependent. We do not know whether that particular image correlates with a particular drug resistance. So there are enormous opportunities.
So we
I
look
think one
forward
can
to you, Sanjay, to
Yeah.
try and contribute to CHAVI and develop the CHAVI microbiology pipeline now.
Thank you very much.
Two specific people, I know we are late. Two specific people, I request you for your comments. One is Rosina. Thank you for coming in. And Rosina, the reason I come to you is because we've been discussing this, isn't it? Mammography, diagnosis of breast cancer, and how we can use big data and AI to try and improve the follow-up and new diagnosis. Any thoughts on how we can link up with CHAVI and what you think about it?
I'm sorry I came in late, so I missed a lot of the meat of what has been presented today. I'm sure once we discuss it, there are a lot of directions we could take. I'm always interested in collecting data on our patients and using that in different ways to analyze it to improve outcomes. I don't want to make much of a comment today, but I'm sure there's going to be something in the future once I've had a chance to maybe see the presentations that were made and understand it in more detail.
Thank you. And finally, we've got someone from the field of imaging who's been tremendous in supporting us. The nuclear medicine department in our institute, they're really, really someone who we can bank on. They're the ones who said, CHAVI, we will be with you. Just go on. And unfortunately, Shomenda, who's the head of the nuclear medicine department, is not here today. He had to attend some other program. But Jayanto is one of our colleagues from nuclear medicine. Dr. Jayanto Das. He's got an interest in predictive models as well. So Jayanto, seeing what you've seen, are you happy with the way that we've collaborated, and how can we enhance it?
Thank you, Dr. Chatterjee. I know we are short of time. Let me explain in very short what will be the implication of CHAVI in our field, in imaging modality. Let me tell one example. There is an eminent respiratory radiologist called Felsen in 18th century who worked on 20,000 chest X-ray to find out one single findings and one single sign, that if you put a organ or a substance which is of equal density of heart, just side of the heart, you will lose the boundary between that particular organ or a particular substance and the heart. That is called, we all know, which is called Silute sign. And to find out this particular sign, he worked on 20,000 chest X-rays on that day. And from that day, imaging has changed a lot from 2-dimensional to 3-dimensional, from 3-dimensional to anatomical plus metabolic imaging, fusion imaging, all and all. And the data which is coming out from the imaging is increasing leaps and bounds. So we all know what is the importance of having data, what is the importance of having the number of images required to find out and to work on the new informations which will be coming out from the imaging. Thank you.
Thank you so much for your support. This brings us to the end of this session, but I believe that the next session, which will be taken forward by Dr. Indranil Malik, my colleague, is the way forward. That's what we are all here to hear. So how do we take this forward? And we've got people who joined from across the country, some virtually. So Indranil, all yours.
It's a huge pleasure to invite a group of panelists that we have all learned from and who will help us take CHAVI forward. Over here in person, I would like to invite Professor J.P. Agarwal on the dais. I would like to invite Dr. A.V. Balachandra and Dr. Abhijit Kaur. Please come, sir. Please come. And virtually, we have colleagues from all over India. We have Professor Sudeep Gupta, the Director of ACTREC and Professor of Medical Oncology at Tata Medical Center. We have Dr. Thomas Ram, the Head of Department of Radiation Oncology at CMC Vellore. We have Dr. Francis James, Professor of Radiation Oncology and Head of Department at RCC Trivandrum.
Thank you.
So let's get started. And I'm just looking for Dr. Shaleen Kumar. Yes, Dr. Shaleen Kumar is the Head of Department of Radiation Oncology at SGPGI in Lucknow. So what are we here for? What is this image bank? Who is it for? It is actually not just for our, the feeling that we are doing something special. The real merit of this image bank will be proven when it actually benefits patients. And so I'll ask the first question to Dr. Abhijit Kaur. Dr. Kaur plays many roles. He is a partner. He works with Dr. Rimpa Achari. He has been treated for a condition in Tata Medical Center. He's also a veterinary surgeon. He heads an insurance agency. So, Dr. Kaur, when patients donate, individuals donate blood, patients donate their samples for biobanking. Now, here we have this concept of an image donation. Now, how image donation is different is that unlike blood, which can finish a sample of blood or a sample of tissue, images can stay. The same image can be used by 1,000 researchers to ask 1,000 different questions. So if we cover the concept of image donation, do you think that it appeals to you as a member of the community and as a patient?
Yes, I feel that it is definitely required to help the society because the peoples of Tata Medical Center as well as IIT, they are helping to develop the images for the betterment of the future, which can be guide properly to the scientists as well as researchers as well as teachers to develop some ways which can help the society for the minimum for minimization of the cost and other things.
Yes. So in fact, what a biobank like this does is that if you have enough images and enough annotations, it can help make faster many of the processes for which there is a lack of staff, there's a lack of technical prowess, a lack of expertise, as many of the colleagues have just mentioned over here. And it is possible that if enough patients come forward to demand that their images are actually used for research, it might open up a completely new door for not just for doctors, but for scientists who are engaging in this kind of activity. So what advice would you give us in terms of reaching out to patients, to potential members of the community to help in CHAVI?
Yes, sir. Those who are coming to take the treatment at Tata Medical Center or other cancer research institute. So from there, we can directly approach that this is the actual our feelings. We can take the help from them, and ultimately, with their consent, definitely we can take.
In fact, when we first started CHAVI, Dr. Kaur, we were a bit skeptical as to what will happen if I hand out an extra consent form to a patient, asking them whether we can archive their images in CHAVI. And we were very reassured to see that practically everybody was not just willing to sign that consent, but actually very excited about providing their images for research. So I think that this is one way of reaching out to a far greater audience than what we currently have. Thank you. We've talked a lot of images, about a lot of computation, etc. But one of the key things that I think as doctors we understand, but we need to communicate it better with computer scientists, is that we often have in usual repositories images and a limited set of clinical data. Now, we as doctors know that the outcomes of a patient don't just depend on those sets of clinical data. There's actually a lot more. And my question is to Dr. James. Dr. James, you are a very busy clinician, and you can appreciate that the clinical data is very, very important along with the images to make a difference in outcome prediction. And in CHAVI, what we have done is that we've tried to make a very structured annotation of clinical data. How important do you think the clinical data is, and how do you think that we can make it more useful in terms of prediction? My question is to Dr. Francis James. Yeah.
I was expecting this will be very helpful for radiomics research and collection of huge data on patients we are treating. For that, the moment we are relying on many data from image banking from international scene, but we don't have much data on Indian patients. So this will be useful for radiomics research, one thing. Secondly, I am thinking very much about unusual cases which are treated in different centers. So if we pull together these cases, we might be able to provide more light into those rare cases. Those were the two things I was thinking more about it.
So when we are annotating clinical data, we have to be careful about de-identification, about maintaining, the temporal sequence of data. And, I think that we've been very fortunate in terms of collaborating with your institution. And do you believe that there is a move to actually work together on common databases in order to make to augment the information that is there in the imaging data?
It will be very useful for all of the people to collaborate and share the data so that we get huge database and we are able to bring out some new findings based on this. And obviously, all the ethics committee, all the permission has to be taken in all centers so that we respect the patient's rights.
Do you have any specific suggestions that on how to how to integrate clinical data into the imaging database?
Yeah, we would be able, after getting consent, we will be able to put in data into the system. Only thing is that we shouldn't be able to recognize patients. And this, when we collect good number of data, we'll be easily able to get into newer observations.
Thank you. We also have in this panel a couple of centers who are actively working on imaging data and AI and trying to build databases. And I'd like to bring in Dr. Sudeep Gupta, who is leading an effort at the moment in Tata Memorial and ACTREC. And we'd like to talk about an imaging partnership. And I'd also engage Dr. JP Agarwal, who is here, to tell us, in a few sentences, tell us about your project and how we can make a complementary input in terms of providing expertise and providing our databases to work together for patients in India.
Good morning, Indranil. Can you hear me?
Yes.
Okay, so thank you very much for inviting me to this excellent program and panel. And my congratulations to yourself, to Sanjoy, to your colleagues from IIT Kharagpur, and to everyone else for making CHAVI possible. And CHAVI is the right and a very evocative name for your efforts, and it absolutely is appropriate for the kind of work that you are doing. At Tata Memorial Center in Mumbai and in ACTREC, we have a DBT supported project to create a cancer imaging biobank, which will include images from pathology and radiology domains, as well as the linked clinical data on two cancers, which is head and neck cancers and lung cancer. And this is a collaborative project of several institutions. We also have Rajiv Gandhi Cancer Hospital in Delhi, All India Institute of Medical Sciences in Delhi, and PGI Chandigarh as our partners. This project started about a couple of years ago, got a little bit derailed because of the COVID pandemic, but is now back on track. We have collected images on a large number of patients, actually for head and neck cancer within Tata Memorial Center. We have about 1,000 patients' images, both radiology, pathology, as well as their clinical information. And we have about 500 images from our partners in other centers. And we are now in the process of setting up the IT infrastructure. It is partly done. And we will hopefully, the remit of our project is not necessarily to do the AI work ourselves, which of course, we and others will undertake, but to provide a biobank of annotated images with linked longitudinal sequential survival type and other data to researchers from all over India. And that is our commitment to the DBT, and we will hopefully fulfill it in the near future. So thank you. And my colleague, Dr. JP Agarwal, who is the head of radiation oncology, is also leading an effort on behalf of the radiation oncology department, which will be extremely impactful and also, in my opinion, very useful for our country. And maybe he will describe it next. Thank you very much.
I'd like to bring in Dr. Agarwal here, although just give me a minute, Dr. Agarwal. I'd also like to move. Acha, the mic is there. Okay, thank you. Yes, Dr. Agarwal. In terms of multi-omic research, when we are talking about multi-omic research, when you're talking about clinical trials, what are your feelings in terms of gathering data? That how can we work together to make, when we run your institute runs a lot of clinical trials, in terms of putting all the clinical trial data, multi-institutional collaborative trial data on image banks, in order to, later do work, answer different questions that we don't know of yet.
Say in first, as a lay human being, I'll take a minute, I think.
Yes.
CHAVI is, as Dr. Gupta said, thank you, sir, very appropriate name. And I sincerely believe it should become like a boy in Bengali, It's a whole movie it should become, right? In my mind, from a black and white images of Satyajit Ray, you should achieve something like my dad used to take me, and my better half is here. Sonar Killa. There was a movie called Sonar Killa, if many of you know that about it. So it should become like that. people should treasure that stuff. That is the actual literally meaning which I believe it should happen. The second part, what you asked, we will be leading at different fronts, different clinical trials of drugs, any intervention or observational studies will come in. Unless until you have a very powerful data, you will not be able to do a hypothesis-led studies, or you need multiple partners to validate that. So this will be an important bank that you have proposed, let's say, imprint or a dosimetric. So the other partners can validate it or invalidate it or improve the internal systems to make it much more robust for our context when we say we have less data. So that's what I lead and I see. The next part is what I think our colleague from the infectious disease wanted: an instant diagnosis. So you need an analyzer. That's what we were talking. So we need to, the first building blocks are there, like you have a bank and a data. Now we need to go forward and think analyzers, AI systems to prove it that it becomes a very robust inbuilt automated system, which we were talking in the morning. So augmented reality becomes a implementable reality from this bank. That's what I perceive in the future.
Thank you, sir. Thank you very much. One of our other colleagues who have joined online is Professor Thomas Ram from CMC Vellore. Professor Ram, your institution also has a keen interest in AI, and you have actually set up an AI center, and we are starting to work on some projects together. Tell us a bit about your AI center and how you're planning to plug in different types of information, genomics or other clinical information into your image bank, and how we can provide complementary inputs into imaging research in India.
Yeah, good morning to all of you. And yeah, first of all, I'd like to thank the CHAVI team for this fantastic work. And I bring greetings from CMC Vellore, and especially from our Department of Radiation Oncology. Yeah, it has been a painful, I can say, journey. But finally, we have our institutional bioinformatics, specially dedicated department and a team which has been set up. And we have a separate dedicated server also installed within the institution, and various departments are plugged into this effort. And one of the major department is from the radiation oncology team. And what we have actually started initiating is some few sites, and I think some of the sites we are already collaborating with TMC Kolkata. And we have a program which is going on in the head and neck cancer. And also we have a small project which is ongoing in rectal cancer and also in the brain tumors. We are also, I would say the different thing about in Vellore, which all of you know, that oncology is only part of the service which Vellore provides. So in this whole initiative, we have multiple specialities who are also plugging into the machine learning and AI facility what we are developing. So that is something different challenge we will face. And we already have a digital pathology team who are plugging into this system. And we have what we have been working within our department, as we heard, is more of a federated learning kind of a concept. And I see a huge possibility of, as various centers develop their own image data bank, and how we can plug in together, and obviously to bridge this whole learning process. And the platform of distributive learning is what I see emerging with this kind of initiatives. The other context of Vellore is what we have is, while we are, the mothership is based in Vellore in the town, now we have multiple campuses. I can say 4 or 5 campuses. Most of them have some kind of imaging, and we have just moved into a new campus. There also we have a lot of imaging happening. So again, physically they are on different sites. So we are networked, and all those images which are captured there, potentially they can be annotated and put in the image bank. Outside Vellore, outside Tamil Nadu, again, we have I can say, network of smaller hospitals in various parts of the country. And some of these have oncology, and most of them have CT scan, at least kind of an imaging. So we're also looking at how we can collaborate with our smaller hospitals, in some of them in rural places, through our network in CMC. So I see a huge potential, and we have been very good, I can say, partners with TMC, and we look forward to this collaboration. Thank you, Indranil.
Thank you. Thank you, Dr. Ram. And you brought in an important point about distributed data sets, federated learning. And I think that I believe it will be useful for all the teams here together to develop ways in which we can develop APIs, for example, where different image banks can communicate with each other. Computer scientists can pull images. The images notations can be harmonized in order to make it more useful for the research community in general, and also to show a sense of community even amongst us, in order to say that instead of competing with each other, we should actually work together to make something which is truly complementary. I would now like to take on a slightly different aspect of the use of an image bank. And that is, we are always talking about AI, and we are talking about, predictions. We are talking about automations and things like that. But really, one of the unspoken of issues about image banking is how it can actually impact treatment quality. And if you have an image bank like we have, where radiotherapy plans, radiotherapy structure sets are put all in one place, it would be a fantastic move to see whether we can improve quality with the help of an image bank. And I'd like the inputs of Dr. Shaleen Kumar, who is particularly interested in this aspect.
Thank you very much, Indranil, Sanjoy, and team for the opportunity to participate in this discussion, and of course, fantastic work. Clearly, I think there is heterogeneity in the way we assess patients, in the way we draw our volumes, in the way the rigor with which we perform quality assurance in the execution of radiotherapy. And there is a huge variability in the country, and even within organizations, you would find variability across physicians. And when we're looking at harmonization, I think the best way out is to get data in one place and then make some sense of the variability, and see what are the commonalities, what are the differences, and make a case for structured education of persons, of stakeholders, physicists, technologists, oncologists, and gently nudge them into rational thinking and also evidence-based approaches. The only way this can happen is, one of the ways this can happen is that they actually participate in this. And I can say that as far as this country is concerned, there is a huge variability there is some variability in infrastructure, but more importantly, some people are absolutely just clinical oriented. There are others into some sort of research, and to get all these people together would be a small challenge, without doubt, but it's eventually going to be very useful. So this concept must be disseminated, and there should be some leeway that all comers participate with different capabilities. I can see, for instance, very clearly that all the major centers that have spoken today have collaborations with industry, and also engineering, and they have very good research programs. Although sitting in SGPGI, we have small islands of excellence, but as an institution, it's 30 years old, but this kind of a structured network is not there. So these challenges are also there. But I guess definitely quality assurance overall, if it has to improve, must be inclusive and take all comers, and people must be willing to learn. That's all I have to add to your discussion.
Thank you, thank you. And we are going to, give you an idea very soon, if you stay on, about a project idea that you may have heard of a collaborative QA program. My final question is to Dr. Balchandra. Dr. Balchandra represents the SERB, and he represents the Indian government in assessing how research should be done, what research should be funded. And I'd like to ask you two quick questions. One is that we, CHAVI and many others are public-facing data repositories. It is open to everybody. Any researcher anywhere in India or abroad can access it. How can government agencies help in promoting these repositories in order for people to start using it, for people to start contributing to it in terms of adding images to it? Is there a way that the government agencies can give some advantages, some special leeway to researchers who actually use and contribute to these registries?
So before moving to the question, I really congratulate the team for this appropriate name, CHAVI. Actually, CHAVI is also another word, is a key to the transformation for the digital health. That's what I, in my perspective, I think in that thing. Regarding that question, what towards the funding possibilities for the repositories and all those things. See, each funding agencies works on the mandate of what it has been created in that thing. In SERB perspective, that's where I can limit myself into that one, since I am representing that thing. So our main thing is to promote the basic R&D activities, in particularly in the field of science and engineering, in all the disciplines, in all the verticals things. And we have nearly 40 different programs and schemes to cater around all the starting from the national postdoctoral fellowships after completing your doctoral thing until after the superannuation thing. There are a number of various programs in that one. But I can highlight a few programs which it can really helps in that direction. Not in terms of repository kind of a thing, but which it can really helps. Actually, when Professor Das, when Sarah was presenting, so that time Sarah has echoed two things. One is that that education and the training part. So we have a special program called Accelerator Vignan thing, where we have programs, two Karyashala programs, where so this type of things where can be appreciated under that kind of a things, where you can bring in young minds and you can house them for 15 days, and then you can teach them, you can show them what is the importance of this in perspectives of AA perspective and also in terms of medical perspectives. That is very, very important. So both the people can understand each the ideas of that things. So that is one thing. Then another thing, so we also have, like the one that impact, that imprint thing. So that is very, very, we are very glad that through that imprint program, so that has led into the CHAVI thing. So that is very, very, we are very happy for that. So that imprint itself, it says that impact in creating that innovation in technology. So that means you are addressing any biological things or anything in terms of engineering perspectives. So that is a very, that is a basic of that program actually. So that is how it has been conceptualized. So that program can be effectively utilized for this kind of activities. And the past 3 years, SERB keeping in the advances of the science and the technology and all those things. So we have keep on evolving with the new programs and schemes. So one, I think I can highlight it. One is that is a profoundness in research activities. So that is, it should not be the regular act, that is any thing that which you are regularly doing, it comes under the ambit of the core research thing. But if you're having anything, something in an out of box thinking, and which it can really have a disruptive ideas, that where it can go fit into a scheme called a supra thing. So which has been 3 years, it has been formulated, and it has been considered as one of the program for the PMO scheme actually. Out of 100 programs, this program has been flagged as one of the thing. And there is another PA program which we have formulated recently. It's called an exponential technology. As the name itself says, that how we can scale up the technology in towards addressing the what we are facing at present.
Thank you. And
so that is the most thing. These are some of the
finally, CHAVI, we are very proud, is an example of a part government funded, part non-governmental hospital funded project, which has actually come to fruition. How can government agencies improve and expand these initiatives? Because it's not just that the people who are interested in this research are only in the government. How can we work together more and more to create new things?
See, as I said, that you can initiate a multi-centric projects where you can bring in people across who have the similar ideas and thoughts, and where it can be applied in an appropriate programs where which we cater into that one. So that is one thing. And when Dr. Sujip sir was mentioning about just a repository where the DBT has funded into that one. So that kind of things that which it should come from the Tata thing on that IIT Kharagpur, and then they can submit a concept note, because I am not a competent person to say that this can be done and all those things, since I am representing on behalf of ACRB. So you can make it as a concept note and you can send it to that appropriate person. So then they can take a call on that one, what it is, that thing.
Thank you very much. I think we've had a number of perspectives on the general aspects and how we can take CHAVI forward. Before we switch off from the panelists, I'd like to request the panelists to stay on while a couple of my colleagues will discuss a project on quality assurance that we have planned to run on the CHAVI platform. So I'd like to invite my colleague, Dr. Moses Arun Singh and Dr. Tapesh Bhattacharya to take this forward.
So a very good morning to all of you. And on behalf of Department of Radiation Oncology, Medical Center, Kolkata, I must thank you all my seniors, colleagues, friends who have come from different parts of the country and making this CHAVI launch successful. I must thank them all. And we must acknowledge and thank all our collaborators in this particular SURAQSA project, starting from SGPGI Lucknow, then CMC Vellore, RCC Trivandrum, MVCCR Kozhikode, and obviously PGI EMEA Chandigarh. And as you know, this is a pan-India initiative. We must welcome all our leading centers from India, and let us work together to make this project forward and make it in a massive one. So recently, just now we have seen that Dr. Shalin was mentioning about the quality assurance, and which is so important for practicing radiation oncology and how CHAVI can take it forward. This is the SURAQSA project, collaborative QA process harmonization for radiotherapy using CHAVI. So we all know that since morning, we are listening how CHAVI can contribute, or CHAVI can contribute in the image-based oncology research. And we have seen different aspects of virtual reality, augmented reality, and all these things. But if we look at the Indian context, what we will find, we'll find that Atomic Energy Regulatory Board of India has shown a benchmark. They have made a very high standard in terms of what I can say, in terms of institutional infrastructure development, in terms of machine installations, in terms of beam profile quality assurance. But what about the patient-specific quality assurance in India? That part is really lacking. And if you see that this need has repeatedly been stressed upon by WHO or World Health Organization to ensure quality and safety. And that comes the importance of SURAQSA project. So what is SURAQSA? It is standardized, unified radiotherapy quality assurance. And you all know that quality assurance is a very important aspect of radiation oncology. Why? Because if we see that radiation oncology is used, more than 50% of patients, of all cancer patients, it is used at any point of time during their treatment. And it is delivered in multiple sessions. And when we deliver this kind of radiation therapy, it actually involves we actually has to identify a particular target area, and then that radiation is delivered in the same area with exactly the same measured and prescribed dose. So if we deviate from that, our whole process will be futile. And there comes the importance of quality assurance in radiation oncology. So what do you mean by quality assurance? It is defined by all those planned and systematic actions necessary to provide adequate confidence that a product or service will satisfy the given requirements for quality quality. And it requires team approach with medical doctors, medical physicists, paramedical staff, combining to work as per set protocols. Standard operating procedures and compliance checks and audits, both at the institutional level as well as the individual level, is possible. And this central radiotherapy trial quality assurance program, like radiation research program in United States, RTTQA in UK, are already existing. So here you can see some dose volume histogram, dosimetric data, and here actually comes the importance of CHAVI and how it can move forward the radiation therapy quality assurance program, that is digitally archived images in the form of CT, MRI, PET-CT, or the digitally archived planning images in terms of DVH volume metrics, which are actually very important for the patient-specific quality assurance program. And there the CHAVI will play an important role, how I will give you a glimpse within a few slides after this. So this kind of international collaborations between different quality assurance groups, they're trying to basically optimize the therapeutic outcome, ensuring the efficacy, and they're trying to make more generalizable data, which has actually led to the formation of global quality assurance of radiation therapy clinical trials harmonization group, which actually this kind of harmonization of quality assurance data will help to reduce the quality assurance related workload for individual centers. It will give you a broader acceptance of the trial results. Stronger statistical power of the trial results can be achieved. So if we see the member of global harmonization, here you can see URTC, RTTQA, JCOG from Japan, TROG from Australia, Canadian Cancer Group, ISRO. But what about India? Yes, we are really lacking. That is, lack of a synchronized radiotherapy quality assurance process across Indian centers mean that India is not represented within this group. So there we thought that we propose to set up India's first central radiotherapy treatment quality assurance program, SURAQSA, within a pilot study. This robust treatment quality assurance will improve outcomes of radiotherapy treatment of various cancers. A centralized quality assurance process will allow basic safety benchmarking across participating centers. So before going to the detail of the SURAQSA project, we must acknowledge all the SURAQSA participating centers, starting from PGI, SDPGI, TMC Kolkata, CMC Vellore, MVCCR Kozhikode, and RCC Trivandrum. But these are all the small steps which we have taken, but we should remember, and we want to welcome all our leading institutes from the country to come together and work forward and make this project a massive and successful one. And here we got the tremendous support from all the participating institutes, which I have already mentioned. So before implementation of the SURAQSA program all over the country, what first we will do, we will go for the SURAQSA pilot project. And this pilot project will be rolled out in the centers who have already participated in the quality assurance program of the high port adjuvant breast cancer trial. And these standard operating procedures from this pilot project will take care of all the aspects of radiotherapy treatment planning and radiotherapy execution across different sites, starting from brain tumors, head and neck, lung, urological cancers, gynecological cancers, and pediatric tumors. So what is the scope of this pilot project? Setting up site-specific pre-radiation SOPs, setting up radiotherapy site-specific SOPs for safe radiation treatment planning processes, setting up treatment imaging SOPs and their use to generate safe institution-specific margins, setting up an external peer review process to drive the quality assurance program, which will ensure transparency from all the centers, identifying areas of collaborative research on each of the cancer sites, integrating with global radiotherapy quality assurance program, which will actually give confidence to the patients, will give confidence to the collaborators, and India can come in the global map of RTQA programs. So once this SURAQSA pilot project starts bearing fruits, and after the tangible documentation of the policy-driven system, after it gets published, we will welcome all the centers from India so that their quality of standard will improve. At the same time, very remotely located centers, faraway places, they can get easy access for their internal audit and under the guidance of the SURAQSA project. And what are the objectives? It develops cancer site-specific radiotherapy standard operating procedures, plan quality assurance for complex plans, manually and recommend areas of non-compliance, determine adherence to harmonized treatment planning goals, pre and post harmonization, and recommend changes when deviation is identified, unified archive of de-identified treatment plans, develop an automated plan review system using DICOM data, of CHAVI with the help of de-identified the images, and which are obviously temporally integrated. There will be possibility of auto plan checking, peer reviewing of the contours, and this part will be taken care of by my colleague Dr. Moses Arun Singh, that how CHAVI can take forward this SURAQSA project. Thank you.
Yeah. Good afternoon, everyone. Dr. Tapesh has nicely laid out what are the possible potential services that would be provided as part of the SURAQSA project. What I'm going to speak about a bit is how CHAVI can lay a platform for this. And when any new center applies to be a part of the SURAQSA project, what they will be having access to is the standardized operating procedures that have already been developed as part of the pilot projects. And as we all know, radiotherapy being a multi-step process, and these quality assurance SOPs will be available for each of these steps. And we, as previous projects, we have been able to develop several softwares, which is one of which is the segmentation platform, which is an online system that is available for that will be available for the participating centers to access. These centers will have access to example contouring guidelines, which they will be able to review, and they will also be able to contour online on example cases which are available there. And from these contours which are done, they will be able to get specific feedback on modifications that they will be able to do. But where exactly does CHAVI fit in the picture? So CHAVI can act as a de-identification platform. The de-identification software that were just demonstrated will be installed in each and every center, participating center, where on their local system, wherein locally the DICOM data of the radiation plans can be de-identified locally, and they can be stored in the CHAVI repository as such. The benefit of having such a repository will be that it gives us the chance to do a blinded peer review of all the contours that are uploaded onto the system. And this will involve also upscaling the available structure of CHAVI to be able to accept and be able to evaluate the DICOM RT plan files within the system itself. And So we will have to, we aim to develop a vendor agnostic software which will be able to evaluate these DICOM-RT plan files. And over a period of time, as we keep doing this, we will be able to develop a multi-institutional library of de-identified treatment plans that are available. And using all these, we will be able to also develop prediction algorithms for all the specific subsites that are involved within the SURAQSA project. And that is how we envision CHAVI to be able to be part of this SURAQSA project at every step of the day, every step of the way. And we envision this as a multi-institutional project. And we aim to use CHAVI as it exists now and also upscale it to be a successful project which will help us to harmonize the quality assurance process for radiotherapy throughout India and take the Indian centers up to par with the international standards.
Thank you, Dr. Moses. Before we end this meeting, I'd like to thank our panelists. Dr. Balchandar, this is one example that I was referring to about multi-institutional quality assurance, and we love to work together with our colleagues in all the institutes and invite more. And we would like to invite all the major hospitals to participate in this project. Thank you very much. Thank you very much. Before we end, I'd like to take a few comments from some of our guests who have come from other institutions. Dr. Selvamani has traveled all the way from Vellore. Dr. Selvamani, you have been a major partner in all our collaborative work. How do you think we should take CHAVI forward? What is something, one tip that you can give us to make it more conducive for multi-institutional research?
One thing is to look at is all institutions are doing individually certain bits. Whether that can be integrated, that will be really good to integrate that together. That will make us, steps forward very quickly than individually working on. So that is how to collaborate that, how to bring in their interest into this. Be the way forward.
Thank you very much. Thank you for coming, ma'am. Dr. Subhash Gupta has traveled from All India Institute of Medical Sciences. We're very grateful, sir, for you to have come here. How can AIIMS and Tata Medical Center, participate in joint projects? You're working with Highport. We would like to invite you again for SURAQSA. How can we work together?
See, we are already working for this Highport project. I'm sure I'll definitely like to work since I'm looking after this brain area and neuro-oncology at All India Institute of Medical Sciences. So I'll definitely like to work upon your other projects like RADGLIO. So it's a beautiful concept. And first of all, I'd like to congratulate the team of this Tata Medical Center as well as IIT Kharagpur for the successful launch of this CHAVI. And I'm sure AIIMS will love to collaborate with your team for their future projects also.
Thank you.
And
finally, we have Dr. Paramita from histopathology. The next step in CHAVI would be to see whether we can integrate histopathology images, microbiology images. And we were hoping that in the collaborative projects that in the prospective studies that we do, whether we can get your histopathology digital images archived for research. You worked in AI. What are your thoughts?
Yeah, definitely. This pathology, AI in pathology has gone very far, and it's time that India catches up with the West. We are already doing multiple collaborative projects with Radboud University, Buffalo University, with and with Tata Bombay also we are discussing. So putting in path images with radiology, with the clinical details, and having an open access data bank, which multiple other institutes across India can participate, do some joint work. It's an exciting area which we would be very happy to contribute to and work for.
Thank you. Finally, before we end, Dr. Sharmila Agarwal, you represent, you don't work in an academic institution, but do you believe that this project can reach out to every institution in the country? And how do you think that whether this project appeals to you?
Thanks, Indranil. Thanks, Sanjay. Thanks, Rima, to inviting me for this today's session. It was really wonderful and a very exhaustive information, which I'm trying to still digest in my brain. It was very interesting when I first got the email about this project and I went through the site. And I was just thinking how we can contribute to this project and also to the two centers which I work, how they can be a part of it. After listening to everybody, what I can think of immediately, maybe the QA part of the radiotherapy planning, which we might be able to or get into. And the later part might be some of the head and neck part and the other programs which you are going to run.
Thank you for your interest. Professor Manjunath, you've traveled all the way from Kharagpur. You have been a tremendous partner in setting up our collaborative work with IIT and SMST. Please, your thoughts on how we can go forward.
So I thank the TMC team for taking this wonderful initiative in establishing the CHAVI project. As you already know that we have the CERCO program with Kharagpur and TMC. In a similar fashion, School of Medical Science and Technology, we offer two different MTech programs, one on medical imaging and image analysis, and other program is on biomedical engineering. In both the courses, we try to address some of the recent challenges on different diagnostic feature extraction from these different imaging modalities. So we could have more interactive establishment, collaborative establishment between these two programs with the CHAVI may support this initiative.
Thank you
So
very
this
much.
is my input.
Thank you. It would be very exciting to take those avenues forward.
Thank you.
I'd like to invite my colleague, Dr. Sanjay Chatterjee, for his vote of thanks.
Thank you all. Before we end, if you can take a group photo for the CHAVI inauguration. I mean, unfortunately, the people who've joined us virtually, grateful that you've joined, sir. It's unfortunately we can't have the photo with you over here now, but thank you for your tremendous support. And thank you again for all of you who've come here. Please get some lunch before you run off to your to whatever you want to do after this. Thank you. So shall we just stand over here for the group photo?
And after the photograph, the lunch is downstairs on the ground floor. So please join us for lunch.